talk is on more efficient functional bootstrapping for general functions in polynomial modulus. And the authors are Han Xiao, Feng Hao Liu, and Han Wang. And the first Han is giving the talk.
So thanks for the introduction. I would like to first introduce some background. So FHE allows arbitrary computation over encrypted data, and FHE ciphers are noisy. That is, as we perform FHE evaluations, the noise grows, and we cannot get the correct decryption result if the noise is too large. So we need bootstrapping. That is to refresh the noise before it becomes too large. And there is a variant of bootstrapping called functional bootstrapping. That is, we not only refresh the noise, but also evaluate a function at the same time. So if the function is identity maps, so they are equivalent. And we may hope that they have similar efficiency even for general functions. So first, let's consider an extractive problem from field and TFHE bootstrapping. That is, if we encrypt alpha in the exponent and times some polynomial v, how do we evaluate the MSB of alpha? So the solution is that we can set all the coefficients of v to 1, and then look at the constant term. And the constant term is determined by the MSB of alpha. So this is sufficient for what we need. And one may ask a more generalized problem. That is, given such an encryption, can we evaluate a function? So there's one solution is just that we can encode the function into the coefficients of v, and then again, we look at the constant term. And we find that there's nothing else to do if f is next cyclic. So the conclusion we can draw here is that functional bootstrapping for next cyclic functions is as efficient as regular bootstrapping over power 2 cyclotomics using the constant sample extraction. However, this is not true for general functions, and there is many attempts to solve this problem, but all these solutions will require at least 2 calls to the regular bootstrapping, and they, some of them require ring extension, and they all work over power 2 cyclotomics, and some have additional assumptions on the input ciphertext. So in our work, we show that functional bootstrapping for general functions can be essentially as efficient as regular bootstrapping, and we do not require ring extension. We can work over quite general cyclotomics, including power 2, and we do not require additional assumptions. To support general functions, we do not use the sample extraction. We just construct a function evaluation algorithm called evalfunc that can evaluate an arbitrary function over the integer rings within a logarithmic complexity if the message is in the exponent of some primitive rule of unity. So in our new workflow, the first step is just to run the regular bootstrapping to get such encryption, and then use evalfunc as a post-processing. So the efficiency of our functional bootstrapping over regular bootstrapping reaches 1 plus little 1. So to construct the evalfunc, we use the technique of homomorphic equality test. And there's a method proposed in Crypto 2014 that works over plain LW. But in this work, we focus on rings. So if we define the equality test as this one, so we found that any discrete function can be written as a linear combination of the equality test. And so the problem is that how to construct the equality test. So let's begin with a simplest case. Over prime cyclotomics, the trace of roots of unity has 2 branches, which is quite close to the equality test. Actually, the trace plus 1 can serve as the equality test. And based on this equality test, we can derive a function evaluation formula. And we can see that in this formula, all the equality tests are performed in parallel. And we only require 1 trace evaluation. But this is not true for general case. For example, if Q is prime power, the trace of roots of unity has 3 branches, which is not satisfactory. But we may consider another equality test proposed in TCC 2021. That is the sum of all possible powers. This equation works for any Q, but the problem is that each equality test requires Q multiplications, and we cannot do all of them in parallel. So to address this issue, let's fix the representative set of dq to be the integers from 0 to q minus 1, and zq star to be the integers in zq, that is co-primed q. So we observe that the index in the equality test is from the set zq, and the index in the trace is from the set ZQ star. So a straightforward idea is that maybe we can bridge this gap by finding relations between ZQ and ZQ star. So our first observation is that we can have a new partition for the Q for prime power Q. So we can just look at this simple example for Q equals to 8. So we have this new partition for the modulo 8. And based on this new partition, we observe that the equality test can be written as a sum of traces. So we only have traces. We only need to evaluate the trace. So to evaluate this trace, we can use the transitivity of the trace. We only need to add the subring or subfield elements into the intermediate results during the evaluation of the trace tower. So all the good things come back. That is, we can do all the equality tests in parallel, and we only need to evaluate the trace of the largest extension only once. So, and moreover, this equality test works for arbitrary prime power, but there's a problem is that we need encryptions of the subring elements. So our result is that this can be done within a logarithmic complexity. So then the overall complexity of function evaluation becomes like this. So next, let's move to the complexity case. So in this case, by the Chinese remainder theorem, two elements modulo Q are equal is equivalent to that they are equal in each CRT branch. So we can just combine CRT with equality test for prime power case. To evaluate this equality test, we can evaluate each CRT branch and then multiply them. But the problem is that the outer product would introduce large noise growth in the FHE domain. So to address this problem, our observation is that for trace or roots of unity, we can factor them. So this equation tells us that we can separate or integrate the traces. So consequently, we can transform the product of traces into the product in the cyclotomic index. And moreover, the equality test, we can transform the product of sums to pure sums. So there's no multiplication at all. We only need to do the sum of traces. But there's a problem is that the trace of sub-extensions are not contained in a single tower down Q. Just consider this example. There's no single line from left to the right that contain all the subfields. So evaluating the traces separately could be quite inefficient. So our solution is that we can just swap the sum and the trace. So this is our final equality test. And in this equality test, we only need to evaluate the trace once. There's also challenge too that we need encryptions of subring elements. And our result is that this can be done within logarithmic complexity if Q is odd and has logarithmic divisors. So the overall complexity of a wave function could be like this. So there's one problem left is that what's the complexity of the trace evaluation? So by definition, the trace evaluation of a Galois group of a Galois extension could be the order of the Galois group. But there exist two methods to accelerate it. The first one is if there exists a tower of field extensions. So in this case, the complexity of trace evaluation becomes a sum of the Galois group of sub-Galois groups. And the second case is cyclic extensions. In this case, the Galois group is cyclic, and the complexity becomes logarithmic. So an important fact is that if the cyclotomic index is the odd prime power, the corresponding cyclotomic extension is cyclic. So our observation is that all the cyclotomic extensions are combinations of the above two cases. So the first, if all the factors are odd primes, so it is just a combination of all cyclic extensions. The second is if it contains some power 2 factors, it is just a combination of the cyclic extensions and a base 2 logarithmic power. So the trace evaluation in both cases only requires log Q automorphisms. And these two cases covers all the possibilities. So our conclusion here is that trace evaluation for arbitrary cyclotomic extension requires logarithmic complexity. So finally, I would like to conclude by two messages to general audiences. So maybe you are not that interested in FPGA bootstrapping, but you do use some homomorphic operations in your program design. So I hope these two small building blocks may be useful for you. The first one is the new homomorphic equality test. So that is, if you encrypt something in the exponent of primitive root of unity, you can check it within logarithmic complexity. And more generally, you can evaluate an arbitrary function over the integer ring, also within logarithmic complexity. So that's all. Thank you.
This is the end of this session. Thank you.